Ultrastructural batteries will replace energy storage and provide tons of energy for everything. Structural batteries are multifunctional composites that combine load-bearing capability with electrochemical energy storage. Instead of having a separate structural skeleton and a separate battery pack, a structural battery merges the two, saving weight and volume, a key advantage in aerospace, automotive, and portable power applications. Basic architecture. A typical structural battery composite consists of three integrated components: electrode fibers, often carbon fibers, CF, that serve dually as mechanical reinforcement and as one of the battery electrodes, typically the anode. In some designs, the CF is coated or intercalated with active materials, silicon, sulfur, or transition metal oxides, to boost capacity. Structural electrolyte, or matrix, a polymer resin that is both ionically conductive and mechanically stiff, a bicontinuous phase of epoxy and ion-conductive polymer, or a ceramic polymer hybrid. This matrix phase binds the fibers together and transmits load, while also allowing ions to shuttle between electrodes. Counter-electrode can be another fiber type, glass or aramid fiber coated with cathode active material, or a foil embedded in the composite layup. Functions electrochemically as the cathode while playing a lesser mechanical role. These elements are laminated together, just like a conventional fiber-reinforced composite, so that mechanical loads, tension, compression, bending, pass through the fibers and the stiff matrix, while ions move through the electrolyte phase to charge or discharge the cell. Electrochemical working principle: charging a voltage is applied across the composite. Lithium ions, in a Li-based system, intercalate from the cathode, migrate through the structural electrolyte, and intercalate into the carbon fiber anode. Discharging the process reverses. Li ions leave the anode fibers, move back through the electrolyte, and reinsert into the cathode. Electrons flow through an external circuit, delivering power to whatever load is attached. Throughout this cycle, the mechanical integrity of the composite remains intact. The fibers and matrix continue to carry loads just as in a conventional composite. Mechanical and electrochemical performance-specific energy. Structural batteries today achieve on the order of 10 to 20 Wh/kg in composite form, compared to 150 Wh/kg for commercial Li-ion cells, but with 50 to 70% of the stiffness and strength of high-performance CF composites. Multifunctionality efficiency, defined as the ratio of weight saved, by merging structure plus battery, to any lost performance. Even a modest multifunctionality, 10%, can justify integration in weight-sensitive platforms. Applications and outlook: electric aircraft. Every pound saved in the structure is a pound less energy needed for lift, critical for eVTOL and drones. Automotive. Integrating the battery pack into body panels or chassis could reduce vehicle mass and improve crash performance. Portable devices. Laptop casings or smartphone frames that also store energy can make gadgets thinner and lighter. Spacecraft. Launch masses at a premium. Structural batteries could cut dozens of kilograms in satellites and probes. Ongoing advances in polymer electrolytes, solid-state materials, and fiber engineering are steadily improving both energy and mechanical metrics. As materials mature and manufacturing scales, structural batteries promise a paradigm shift in how we think about energy storage and load-bearing components, turning passive deadweight into active, power-delivering elements. Structural batteries are advanced materials that serve two main functions at the same time. They can store electrical energy like a traditional battery, and they can also carry mechanical loads like a structural component. This dual functionality allows them to replace both the battery pack and structural parts in systems such as electric vehicles, aircraft, and portable devices, thereby reducing overall weight and volume. Structure and composition: a structural battery is typically made up of three key components: electrode fibers, a structural electrolyte matrix, and a counter-electrode. These components are assembled in a layered composite, much like traditional fiber-reinforced materials used in aerospace or automotive engineering. Electrode fibers often consist of carbon fiber. Carbon fiber is strong, stiff, and conductive, which makes it ideal for serving both as a mechanical reinforcement and as an electrode, usually the anode, negative electrode, in the battery. In some designs, these fibers are also coated or infused with additional active materials to increase their energy storage capacity. The structural electrolyte is a specially engineered polymer or composite material that can conduct ions while also remaining stiff and durable enough to bear mechanical loads. This matrix binds the fibers together and allows lithium ions, or other charge carriers, to move between the electrodes during charging and discharging, just like in a traditional battery. The counter electrode, or cathode, may be made from a different type of fiber or a coated metal foil. It completes the electrochemical circuit while also contributing, to some extent, to the material's mechanical performance. Together, these elements form a multifunctional composite that can simultaneously support mechanical stress and facilitate electrochemical reactions. How structural batteries work during charging. A voltage is applied across the structural battery. Lithium ions leave the cathode and move through the electrolyte toward the carbon fiber anode, where they are stored. At the same time, electrons flow through an external circuit to complete the charging process. When the battery is discharging, the process is reversed. The lithium ions leave the anode, travel back through the electrolyte to the cathode, and electrons flow through an external circuit to deliver power to a connected device or system. Throughout this entire process, the composite continues to function as a structural material. It carries mechanical loads such as tension, compression, or bending, just like a traditional carbon fiber composite. Material challenges and trade-offs. Designing structural batteries involve several important trade-offs. For example, increasing the ionic conductivity of the structural electrolyte may reduce its mechanical strength, while making it stiffer could impair ion movement. Similarly, while carbon fibers are excellent mechanical reinforcements, they do not store as much energy as traditional battery materials, so enhancements are often needed to increase their electrochemical performance. Performance characteristics. While structural batteries currently have lower energy densities, typically around 10-20 watt-hours per kilogram, than conventional lithium-ion batteries, which can reach 150 to 250 Wh/kg, they offer significant system-level benefits. Because they can replace structural elements, they reduce the need for separate battery packs and support structures, saving overall weight and volume. Moreover, the best structural battery composites today retain about 50 to 70% of the stiffness and strength of high-performance carbon fiber composites, while also providing usable energy storage. This multifunctionality is particularly valuable in systems where weight and space are critical, such as electric aircraft or space vehicles. Applications and future outlook. Structural batteries have many promising applications. In electric aircraft, they can reduce the overall weight, making flight more energy efficient. In automobiles, structural batteries could be built into the car's body panels or chassis, helping to extend driving range without increasing vehicle mass. Portable electronics could also benefit from casings that double as batteries, making them thinner and lighter. Even in spacecraft, where launch mass is extremely costly, structural batteries could significantly reduce the weight of satellites and probes. While the technology is still in its early stages of development, advances in materials science, particularly in solid-state electrolytes and functional fibers, are steadily improving both the mechanical and electrochemical performance of structural batteries. As these materials continue to evolve, structural batteries are expected to play a significant role in the design of next-generation vehicles, electronics, and energy systems. Structural batteries are an active area of research and development, and while they are not yet widely commercialized, several organizations and companies are working on prototypes and early-stage integration in real-world applications. In development or prototype stage. Volvo Chalmers University of Technology, Sweden. Volvo and researchers at Chalmers developed a structural battery prototype integrated into car body panels. Carbon fiber acts as both reinforcement and an electrode, while a solid polymer electrolyte conducts ions. Early prototypes had modest energy densities, 20 watt-hour per kilogram, but demonstrated structural functionality, could eventually replace parts like the roof or trunk lid in electric vehicles. Base Systems. University of Michigan. Military applications. Structural batteries for lightweight drones and soldiers' gear. Reduce weight while maintaining durability and operational runtime. Allows equipment to be lighter and more power efficient without sacrificing strength. Airbus. European Union projects. Clean Sky. Research into structural batteries for aerospace applications. In aircraft, reducing weight even slightly translates into huge fuel savings or improved range. Still in lab or proof of concept stages, but promising for future electric aviation. NASA. Boeing, early research stage, spacecraft and satellite applications, where weight reduction is extremely valuable, could lead to spacecraft hulls that also store energy for onboard systems. University research initiatives. Chalmers University, Sweden, is one of the leaders, having built structural battery composites with 10 times better mechanical properties than earlier designs. Imperial College London and MIT are also developing new multifunctional polymer composites for aerospace and automotive use. KTH Royal Institute of Technology has worked on load-bearing electrolytes with both high stiffness and good ionic conductivity. Not yet commercially available, but coming. No consumer products currently on the market use structural batteries as a core energy solution, at least not in a form where the structure significantly replaces the traditional battery pack. The main reasons are low energy density compared to commercial lithium batteries, complex manufacturing processes that are still being refined, material trade-offs between stiffness and conductivity that are not yet fully optimized. Can cars or buildings be made with structural batteries in the future? Both cars and buildings could potentially be made with structural batteries in the future, though each application has unique challenges and opportunities. Here's how this could play out. Cars with structural batteries. Why it makes sense. Weight reduction, one of the biggest benefits. Structural batteries allow you to eliminate the heavy, centralized battery pack and instead distribute energy storage through body panels, chassis components, or even the floor. Space savings. Integrating batteries into structural parts frees up interior space for passengers or cargo. Improved efficiency. Lighter vehicles require less energy to move, which can improve range or reduce fuel electricity use. Possible integrations. Door panels, roof and trunk lid, floor pan or firewall, structural members in the chassis, cross beams. Current status. Companies like Volvo, Tesla, in concept form, and startups have expressed interest in integrating battery functions into structural car parts. Tesla's structural battery pack, in the Model Y Texas version, is a step in this direction. While not a full structural battery, it integrates the battery pack into the car's frame to enhance stiffness and reduce weight. Buildings with structural batteries. Why it could work. Distributed storage. Energy storage could be spread throughout walls, floors, or roofs, ideal for smart homes and solar-powered buildings. Aesthetics and integration. Instead of a big battery in the basement, the walls themselves could help power your home. Grid independence. Structures with embedded energy storage can act like self-contained energy hubs, enhancing resilience and reducing peak demand on power grids. Possible use cases. Concrete panels infused with battery materials. Walls or floors made of carbon fiber composites, more likely in high-end or commercial structures. Smart facades that combine solar capture and energy storage. Research is ongoing, especially in concrete-like structural batteries, cement-based materials doped with conductive and electrochemical additives, carbon fiber sandwich panels for architectural and commercial applications. As materials science advances and sustainability becomes more urgent, structural batteries could fundamentally change how we design cars, homes, and cities. Structural batteries in cars. Structural batteries have significant potential in the automotive industry because they can reduce both the weight and volume of electric vehicles by integrating energy storage directly into the structure of the car. This means that parts of the vehicle such as the doors, roof, chassis, or floor could not only provide mechanical support, but also store and deliver electrical energy. Why this matters for cars and electric vehicles. A large portion of the weight comes from the battery pack. By replacing passive structural components with materials that can also store energy, automakers can save weight and free up space, which leads to improved driving range, better handling, and potentially lower production costs over time. For example, instead of mounting a heavy lithium-ion battery pack under the floor, engineers could design the floor itself to act as a load-bearing battery. Current development. Several companies and research institutions are actively working on this concept. For instance, Volvo, in collaboration with Chalmers University of Technology in Sweden, has created prototype car body panels that can store energy like a battery. Tesla has also introduced a design called the structural battery pack in certain Model Y vehicles produced at its Texas Gigafactory. While this pack doesn't function as a structural battery in the full sense, it represents a step toward integrating the battery more closely with the car's frame to improve structural integrity and reduce parts. Challenges to overcome. Despite the promise, there are significant technical challenges to overcome before structural batteries can be used widely in vehicles. One major issue is safety. In a car crash, structural components must absorb impact forces without causing the battery to short circuit or catch fire. Durability and repairability are also concerns, since replacing or repairing a structural battery is more complicated than servicing a traditional battery module. In addition, manufacturing processes for structural batteries are more complex and expensive than conventional methods. Structural batteries in buildings. Structural batteries also hold promise for future buildings, particularly in the context of sustainable architecture and smart energy systems. The idea is to create building components, such as walls, floors, or roofing materials, that not only support the building physically but also serve as energy storage devices. Why this is beneficial: buildings increasingly rely on distributed energy systems like solar panels. With structural batteries, the energy generated from solar panels could be stored directly within the walls or floors, instead of in a separate battery unit. This approach can reduce the need for bulky external batteries and make better use of space, while also offering greater resilience during power outages. Potential use cases: in the future, we may see concrete panels or carbon fiber composites embedded with battery materials used in commercial or high-performance residential buildings. These multifunctional building elements could store energy and deliver it to the building's electrical systems when needed. For example, a smart wall might collect solar energy during the day in power lighting or appliances at night. Key limitations and barriers: however, several barriers must be addressed before this technology becomes viable in the building industry. First, materials like carbon fiber, commonly used in structural batteries, are currently too expensive for widespread use in most construction projects. Second, buildings have much longer expected lifespans than batteries, often lasting several decades, while most current battery technologies degrade after about 10 to 15 years. There are also regulatory hurdles, as building codes and fire safety standards do not yet account for structures that incorporate energy storage within load-bearing elements. Developing safe, long-lasting, and affordable structural batteries for buildings will require significant innovation in materials and design. Both cars and buildings could be constructed using structural batteries in the future. For electric vehicles, structural batteries offer a way to reduce weight, improve energy efficiency, and optimize space. Some companies have already produced working prototypes, and further development could make this a standard approach in automotive design. For buildings, structural batteries represent an innovative path towards sustainable and energy-independent architecture, especially when integrated with renewable energy sources like solar panels. However, widespread adoption in either sector depends on overcoming major technical, safety, and regulatory challenges. As research progresses and materials improve, structural batteries could play a key role in the next generation of vehicles and infrastructure. What technologies can be integrated with structural batteries? Structural batteries are versatile by nature, and their multifunctionality makes them an excellent platform for integrating with various technologies across materials science, energy systems, and electronics. Below is a comprehensive overview of the technologies that can be integrated with structural batteries, along with how and why they work well together. Renewable energy technologies: solar panels, structural batteries, can be paired with photovoltaic cells to store solar energy directly in the same structural unit. In vehicles, like solar cars, or buildings with solar facades or rooftops, solar panels could charge structural batteries embedded in walls, roofs, or body panels. Eliminates the need for bulky external batteries and streamlines energy capture and storage in a compact, space-efficient form. Advanced materials and nanotechnology: multifunctional carbon fibers. Carbon fibers can serve both as mechanical reinforcements and as electrodes in the battery. Nanotechnology enhancements: graphene coatings to improve conductivity, silicon nanoparticles to increase energy density, carbon nanotubes for enhanced strength and surface area, boost both the structural and energy storage capabilities simultaneously. Solid-state electrolytes replace liquid electrolytes with solid ones that are safer and can bear mechanical loads, enables safer integration in load-bearing structures, and is more resistant to fire or leaks, especially important in vehicles and buildings. Embedded sensing and Internet of Things: smart materials and embedded sensors, strain, temperature, pressure, or chemical, can be embedded directly into the structural battery. In aerospace, detect stress or damage in wings that also store power. In buildings, monitor structural health while powering embedded lighting or climate control systems. Creates self-sensing, self-powering structures with real-time monitoring capabilities. Wireless energy transfer and communication: incorporate wireless charging coils or communication modules, like BLE, LoRa, or NFC. Drones or vehicles with parts that wirelessly transmit power to smaller systems, e.g., cameras, sensors, without additional wiring. Mobility and lightweight vehicle systems: electric vehicle drive systems, powertrains, motors, and control systems can be powered by and physically anchored to structural battery modules. Body panels or floors that both store energy and form the skeleton of electric cars or aircraft. Reduces vehicle mass and increases energy efficiency, potentially extending range and reducing material use. Building technologies. Energy-efficient building envelops walls, roofs, or structural beams that integrate thermal insulation with structural battery materials. Smart homes or buildings that store renewable energy and regulate temperature using integrated systems. Enhances energy resilience and space efficiency in green building design. Thermoelectric materials incorporate materials that convert heat into electricity, thermoelectrics, into structural battery systems. Captures ambient or waste heat, e.g., from machinery or sunlight, and charges the structural battery. Improves overall energy capture and utilization efficiency. Aerospace and defense technologies. Load-bearing avionics and composites use structural battery composites in aircraft wings, drone bodies, or satellite frames to both power and support flight systems. Reduces launch weight, increases endurance, and enhances functionality in space or airborne vehicles. Camouflage and active surfaces. Power dynamic camouflage systems, or active surface coatings, using embedded energy from structural batteries. Military uniforms, drones, or tanks with integrated energy and adaptive skins. Reduces external power needs and increases operational stealth and flexibility. Manufacturing and additive technologies. 3D printing and multi-material additive manufacturing use 3D printers to deposit structural battery materials directly into the product during manufacturing. Enables custom geometries and integrated functions in drones, vehicles, and tools with minimal waste. Technologies that can be integrated with structural batteries. Comprehensive explanation in complete sentences. Structural batteries can be combined with many other technologies to create multifunctional systems that store energy, carry loads, sense their environment, and interact with other devices. Below I explain, in complete sentences, the main technology categories that can be integrated with structural batteries, how the integration works, and what benefits or challenges each pairing presents. Photovoltaics. Solar panels can be integrated with structural batteries so that energy from sunlight is captured and stored directly within the structural components of a vehicle or building. In this arrangement, photovoltaic cells mounted on or embedded in a facade, roof, or vehicle can generate electricity and feed it into the structural battery, which stores the generated energy for later use. This integration reduces the need for separate battery enclosures and can improve system-level energy efficiency, but it requires electrical interfaces and power management electronics to handle variable solar inputs and to protect the battery from overcharge. Thermoelectric modules can be combined with structural batteries to harvest waste heat and convert it into electrical energy that the structural battery can store. This approach allows ambient or operational heat, such as sunlight-warmed surfaces or engine heat, to be partially recovered and retained within a structure, improving overall energy utilization. Integrating thermoelectrics requires thermal coupling and careful temperature management so that the structural battery materials do not degrade from excess heat while still delivering meaningful electrical power. Solid-state electrolytes and solid-state battery chemistries are natural partners for structural batteries because they remove flammable liquids and improve mechanical stability. Solid electrolytes can be engineered to be mechanically robust and to form part of the load-bearing matrix, which reduces the risk of leaking, thermal runaway, and fire. The main challenges in using solid-state chemistries are manufacturing complexity, ensuring sufficient ionic conductivity at operating temperatures, and maintaining good interfacial contact between electrode fibers and the solid electrolyte. Advanced carbon-based and nanomaterial electrodes can be integrated into structural batteries to increase energy density while retaining structural performance. Examples include carbon fibers functionalized with graphene, carbon nanotubes, or silicon nanoparticles that increase surface area and reversible capacity. These materials improve the electrochemical performance of structural electrodes, but they can complicate composite processing and sometimes reduce fiber-to-matrix adhesion, so advanced surface treatments and scalable coating methods are required. Embedded sensors and Internet of Things (IoT) devices can be integrated into structural batteries to enable real-time structural health monitoring and energy management. Strain gauges, temperature sensors, moisture detectors, and electrochemical state sensors can be co-located with the energy-storing elements so that the system can report mechanical loads, detect damage, and optimize charging or discharging based on structural condition. Embedding sensors requires low-power electronics, robust communication links, and protection strategies so that sensing hardware does not compromise the structural or electrochemical integrity. Power electronics and battery management systems can be integrated into the structure or distributed across structural battery modules to manage charging, protect against faults, and optimize cell balancing. These electronics include DC-DC converters, battery management circuits, and safety disconnects that must be thermally managed and mechanically secured. Integrating power electronics reduces wiring complexity and can improve reliability, but it raises issues about maintenance, access, and electromagnetic compatibility that must be addressed at the design stage. Wireless charging and wireless power transfer can be combined with structural batteries to enable contactless charging and reduce connector wear. Inbuilt environments or vehicles, coils or resonant power transfer systems embedded in walls, floors, or body panels can charge structural batteries without physical plugs. This capability simplifies user interaction and can enable opportunistic charging, but it requires careful alignment, shielding to avoid interference with other electronics, and measures to limit stray electromagnetic fields for safety. Thermal management systems and phase change materials can be integrated with structural batteries to control operating temperature and improve life cycle. Active cooling channels, heat pipes, or passive phase change inclusions embedded in structural layers help maintain the battery within optimal temperature windows and mitigate degradation during high-power operation. The trade-off for thermal management is added mass, complexity, and sometimes reduced mechanical stiffness if cooling pathways interrupt continuous fiber architecture. Additive manufacturing and multi-material 3D printing can be used to fabricate structural batteries with complex architectures and graded properties that optimize both mechanical strength and electrochemical function. These manufacturing approaches enable precise placement of active materials, current collectors, and reinforcing fibers, which can improve multifunctional efficiency and reduce waste. Challenges include scaling the process to large parts, achieving consistent material properties, and qualifying printed parts for safety-critical applications. Energy harvesting surfaces and active facades can be integrated with structural batteries so that building envelopes or vehicle exteriors continually capture energy from wind, vibration, or motion. Piezoelectric elements, small wind generators, or vibrational harvesters can feed small but steady power into the structural battery, improving autonomy for sensors in low-power systems. Integrating harvesting devices requires mechanical coupling and may change dynamic behavior under loads, so designers must account for added vibrations or fatigue paths. Structural health and safety systems, including fire suppression and fault isolation, can and should be integrated with structural batteries to address the increased risk profile of embedded energy storage. For example, fire-retardant layers, ceramic separators, pressure relief features, and current interrupt devices can be built into structural battery modules to limit propagation of faults. Including these systems adds weight and complexity, but is essential to meet safety standards and to gain regulatory acceptance for vehicles and buildings. Recycling and end-of-life management technologies must be planned together with structural batteries so that materials can be recovered and replaced without destroying the host structure. Modular design strategies, demountable layers, and chemical processes tailored to composite battery chemistries facilitate reclamation of valuable fibers and electrode materials. Ensuring recyclability often competes with the desire for continuous, high-strength laminates, so designers need to balance circular economy goals with mechanical performance. Integration with grid and microgrid controls allows buildings or fleets of vehicles with structural batteries to act as distributed energy resources that participate in demand response and grid services. Structural batteries that communicate with energy management platforms can charge when electricity is inexpensive or abundant and discharge during peaks, which provides value beyond the host structure and can justify higher initial costs. This integration requires secure communications, standard protocols, and regulatory frameworks for aggregated controls. Applications in mobility, aerospace, and architecture combine many of the above technologies into specific system architectures that exploit the unique advantages of structural batteries. For example, an electric aircraft wing might integrate carbon fiber electrode laminates, embedded sensors, solid-state electrolytes, and dedicated thermal pathways, while an energy-positive facade for a building might combine photovoltaics, structural battery panels, and wireless communications. Each application imposes different constraints on weight, safety, lifespan, and maintainability, which drive the choice and integration depth of supporting technologies. Finally, standards, certification processes, and new building and vehicle codes will need to be developed in parallel with technology integration in order to ensure safety, interoperability, and public acceptance. Regulatory work is as essential as materials research because embedding energy storage into load-bearing structures changes failure modes and repair practices, and it requires new inspection, testing, and emergency response procedures. How to build a car with structural battery. Building a car with a structural battery is an ambitious engineering process because the vehicle must combine energy storage, mechanical strength, safety, and manufacturability into the same components. Below is a comprehensive, step-by-step explanation in complete sentences of how such a vehicle can be designed and built. The first decision is determining how deeply the structural battery will be integrated into the car. There are three main approaches. Semi-structural, the battery pack is integrated into the frame for stiffness, like Tesla's structural battery pack, but the cells themselves are not load-bearing. Structural composite battery panels, car body panels or floor elements both hold energy and contribute to strength. Fully structural battery monocoque, the entire chassis is a battery containing composite structure, the most advanced and future-level approach. For now, most practical systems fall into the second category, body and chassis parts reinforced with energy-storing fibers. To build a structural battery, three material systems must work together. Structural electrode, usually the anode carbon fiber, is ideal because it is strong, lightweight, conductive, and can store lithium ions. It can also be coated with silicon or graphene to increase energy capacity. Structural electrolyte matrix, a solid or polymer-based electrolyte is needed that can conduct lithium ions, but also function like a strong composite resin. Examples include epoxy mixed with lithium-conducting polymers, ceramic polymer solid electrolytes, safer, non-flammable, but continuous structural electrolytes, stiff plus ion conductive at the same time. Cathode integration. The positive electrode is more challenging to integrate structurally, so two methods are used: coating structural fibers, e.g., aluminum-coated glass fiber, with cathode materials embedding thin cathode foils or meshes within composite layers. Engineer the composite battery chassis. The floor, skateboard platform, is the most important component. Manufacturing steps: lay carbon fibers in load-bearing orientations, similar to aerospace composites. Coat or treat fibers so they act as the anode for lithium-ion storage. Insert separator layers to prevent electrical shorting. Integrate cathode-coated layers or foils in alternating laminate layers. Infuse the entire structure with a solid structural electrolyte resin that binds the material like glue. Conducts lithium ions between electrodes. Cure the composite under heat and pressure to create a stiff, monolithic battery structure. The result is a rigid vehicle floor that acts like a giant, flat battery cell. Integrate battery management and power electronics. Because the structure now stores energy, electronic integration must be distributed rather than centralized. Required systems include battery management system, BMS to monitor temperature, voltage, and charge balance. Embedded current collectors built into the structure. High voltage contacts at safe structural nodes. Fuses and isolation switches for crash safety. Lightweight wiring or printed conductive pathways. Unlike a traditional battery, the energy storage system now spans the length of the car, so wiring must be minimized and carefully shielded. Implement thermal management. Structural batteries cannot overheat, so cooling must be built directly into the design. Common approaches: thin liquid cooling channels laminated into the composite graphene or aluminum heat spreading layers. Phase change materials that absorb excess heat. Passively airflow channels integrated into underbody design. This ensures the structural battery stays within safe operating temperatures without compromising rigidity. Ensure crash safety and electrical isolation. Since the battery is part of the structure, crash safety must be engineered differently. Solutions include embedding ceramic separators or solid electrolytes to prevent fires, designing electrical isolation zones that cut power in milliseconds during impact, making front and rear crumple zones non-electrical, battery only in central protected areas, using fire-retardant composite layers. The goal is to make sure the car crumples safely without rupturing or short-circuiting the energy-storing structure. Assemble the rest of the vehicle around the structural battery. Once the floor or panels are complete, the rest of the car is built similarly to modern EV manufacturing. Motors mounted to subframe, suspension attached to strong battery chassis, anchor points, drivetrain wired into high-voltage structural terminals, interior and body panels mounted as usual because the car no longer needs a separate battery pack. Overall weight and part count are reduced. Benefits: a successful structural battery car would be lighter than conventional EVs, have increased driving range without larger batteries, require fewer parts and less raw material charged like a normal EV, but use its structure to store power, offer higher chassis stiffness, and better handling. Be redesigned around multifunctional materials instead of separate components. Structural battery vehicles combine two functions into the same components by making some or all of the load-bearing parts of the car also store electrical energy. The objective of using structural batteries in a car is to reduce total vehicle mass, save space formerly occupied by a separate battery pack, improve packaging flexibility, and potentially increase vehicle range or performance per unit mass. The most practical near-term approach is to build a skateboard or floor structure that is both the primary chassis and a large, flat battery cell, while retaining traditional non-energized crumple zones to preserve crash safety. The first major step in the project is to define the integration strategy and system architecture. The design team must decide whether the vehicle will use semi-structural integration, in which a conventional battery pack is mounted into a structural frame, structural panels, in which certain body panels or the floor store energy, or a full structural monocoque, in which nearly the entire chassis contains electrochemical materials. The choice of strategy determines how much of the car's mass and volume will participate in energy storage, and it strongly influences manufacturability, safety engineering, repairability, and regulatory compliance. Selecting materials is the next critical step because the materials must deliver both mechanical performance and electrochemical function. Carbon fiber is the most common structural electrode material because it already provides high stiffness and strength while also conducting electrons and, in some chemistries, intercalating lithium ions. The structural matrix must be a solid or gel electrolyte that provides sufficient ionic conductivity while retaining high modulus and toughness, and candidates include the continuous polymer electrolytes, ceramic polymer hybrids, or specially formulated thermosetting resins that incorporate ion-conducting phases. Cathode functionality can be provided by coated fiber layers, embedded thin foils, or separate cathode plies, and all electrodes must be separated by physically robust, electrically insulating separators to avoid short circuits under mechanical stress. Designing the vehicle layout requires identifying which parts will safely and effectively store energy. The floor or skateboard chassis is the highest priority because it is large, relatively protected from direct frontal or rear impacts, and centrally located for good vehicle dynamics. Roofs, doors, and non-crumple cross members are secondary candidates because they can add distributed energy capacity without dramatically altering crash behavior. Bumpers, crash boxes, and other sacrificial deformation zones should generally be excluded from energy storage because predictable mechanical failure in those parts is a key safety mechanism that must not be compromised. The manufacturing process adapts composite production techniques to include electrochemical assembly steps. The process typically includes carbon fiber layup with electrode treatments or coatings, insertion of cathode and separator layers in precise sequences, infusion with a solid or gel structural electrolyte, and curing under heat and pressure to form a monolithic laminate. Quality control during layup and curing must ensure uniform electrolyte distribution, intimate contact between electrode layers and the electrolyte, and the absence of voids that would reduce mechanical or electrochemical reliability. Tooling must be designed to handle electrical connections and to allow safe handling and assembly of energized components. Battery management, power electronics, and current collection must be integrated into the structure in a way that preserves mechanical continuity while allowing safe electrical operation. The vehicle needs a distributed battery management system that monitors cell voltages, current flows, temperature, and state of charge across the large structural cell network. Current collectors and high-voltage junctions must be mechanically anchored to the chassis at secure points that maintain electrical isolation from exposed metal and that include fast-acting disconnects for emergency scenarios. Power electronics such as DC-DC converters and contactors may be embedded in protected housings bonded to the chassis or located in serviceable modules that connect to the structural battery through sealed interfaces. Thermal management must be built into the structural design because it affects both battery life and safety. The chassis should include integrated cooling channels, heat-spreading layers, or phase change materials as needed to keep the cell within safe operation temperatures during charging, discharging, and thermal abuse conditions. The cooling approach requires a careful trade-off between added mass and thickness and the thermal performance benefit, and designers must ensure that cooling channels do not produce stress concentrators that reduce fatigue life or compromise crashworthiness. Crashworthiness and electrical safety require specialized engineering to ensure that mechanical deformations do not produce electrical faults that could cause fire or electrocution. The vehicle must retain conventional crumple zones that are entirely non-energized so that predictable energy absorption is preserved. The structural battery region should be placed in protected central locations and should include internal ceramic separators, fire-retardant layers, current interrupt devices, and overpressure venting where necessary. Crash sensors and automatic isolation systems must be able to disconnect the structural battery from the vehicle's electrical system immediately after a severe impact to prevent secondary hazards. Testing, validation, and certification are extensive and multidisciplinary because structural batteries alter both mechanical and electrochemical failure modes. Mechanical testing programs must include quasi-static strength tests, fatigue tests, torsion, bending, and localized indentation to simulate stone impacts and tool strikes. Electrochemical testing must include cycling under different mechanical load states, abuse tests for overcharging and thermal runaway, accelerated aging to predict calendar life, and combined load and cycling tests to evaluate degradation mechanisms. Full vehicle crash testing, including post-crash electrical safety evaluations, is essential to satisfy regulators and to prove safe behavior in real-world scenarios. Maintenance, repair, and servicing strategies must be developed in parallel with the vehicle design because embedded batteries complicate traditional repair workflows. The vehicle architecture should favor modular and demountable structural battery panels in high-risk regions so that damaged sections can be removed and replaced without destroying the rest of the chassis. Service procedures must be defined for safely isolating and removing panels, for testing residual charge, and for handling end-of-life components. Training and tooling for repair technicians are necessary to prevent mishandling of energized structural parts. End-of-life management and recycling considerations must be included from the first design phase because structural composites and battery chemistries alike contain valuable and potentially hazardous materials. Designers should plan for disassembly routes that allow recovery of carbon fiber, metals, and electrode materials, and they should consider chemical recycling methods or mechanical separation techniques that minimize loss of fiber properties. Designing for circularity often means accepting some compromises in continuous laminate performance to enable demountable joints, sacrificial bolt interfaces, or connectorized panels. Cost, supply chain, and scalability are practical constraints that determine commercial viability. Carbon fiber and advanced solid electrolytes are more expensive than conventional battery materials and stamped steel structures, so early adopters are likely to be high-value applications such as premium electric vehicles, aerospace, or defense where kilograms saved have high economic value. Scaling production requires investment in composite manufacturing capacity, in new tooling that handles electrochemical assembly steps, and in suppliers capable of producing electrodes and solid electrolytes to automotive quality and throughput. A realistic deployment pathway proceeds from demonstrator prototypes to low-volume production of specialized models, and finally to scaled integration as materials costs fall and manufacturing processes mature. Initial commercial vehicles will likely use partially structural approaches, such as integrating battery modules into structural frames or using energy-storing panels for non-crash critical parts. And later generations will increase the fraction of structure dedicated to energy storage as reliability, safety, and cost metrics improve. A hypothetical example clarifies the trade-offs involved. A mid-size electric car that replaces a 500 kg conventional battery pack with 300 kg of structural battery floor and panels might reduce vehicle mass by 200 kilograms while delivering an energy capacity that is, for structural battery chemistry, lower per kilogram than a pack. The system-level benefit comes from eliminating separate battery enclosures and structural reinforcements, which can increase overall energy per vehicle mass. Even if the specific energy of the structural material is modest, quantitative performance will depend on the specific electrode coatings, electrolyte conductivity, mechanical layup, and the fraction of the vehicle that is electroactive. In summary, building a car with structural batteries requires integrated systems engineering that balances mechanical performance, electrochemical function, safety, manufacturability, repairability, and recyclability. The most practical near-term implementations focus on central, protected chassis elements such as the skateboard floor and selective panels, and the roadmap to broader adoption depends on advances in solid electrolytes, scalable electrode treatments, and changes to standards and repair infrastructure. The endeavor combines composite engineering, battery science, vehicle safety design, and systems integration in order to produce vehicles that are lighter, better packaged, and energetically more efficient while meeting strict safety and serviceability requirements. How can we integrate structural batteries into phones, electronics, buildings, cars, trains, aircraft, cities, transportation systems, and every other thing that's functional? Integrating structural batteries everywhere. Integrating structural batteries across devices, vehicles, buildings, and infrastructure requires rethinking how we design, manufacture, certify, maintain, and recycle almost every functional object. Below I describe general principles that apply to all scales, followed by specific integration strategies and trade-offs for phones and small electronics, buildings, cars, trains, aircraft, city infrastructure, and transportation systems. I finish with a phased rollout pathway, the main technical and non-technical enablers, and the safety, repair, and end-of-life considerations that must accompany any large-scale deployment. General principles for universal integration: structural batteries must be designed as multifunctional systems in which mechanical, electrochemical, thermal, sensing, and safety functions are co-engineered. Integrating energy storage into load-bearing elements means balancing competing requirements so that neither structural performance nor battery performance is unacceptably compromised. Designers should adopt a systems engineering approach that treats the structure, energy storage, power electronics, thermal management, sensing, and maintenance access as one integrated product rather than a stack of independent subsystems. To achieve commercial viability and safety at scale, integration must be accompanied by standards for testing and certification, modularity for repair and recycling, and manufacturing processes that meet throughput and cost targets. Core enabling technologies and methods: multifunctional materials, materials that simultaneously provide mechanical strength, ionic electronic induction, thermal conductivity, and environmental resistance are essential. These include carbon fiber electrodes, graphene or CNT enhancements, ceramic polymer solid electrolytes, and continuous polymer matrices that retain stiffness while conducting ions. Solid or semi-solid electrolytes. Solid electrolytes reduce fire risk and allow load-bearing electrolytic matrices to be used in structural parts. These electrolytes should have sufficient ionic conductivity at operating temperatures and strong interfacial adhesion with electrode fibers. Embedded sensors and BMS. Distributed sensor networks integrated into structural laminates allow continuous monitoring of temperature, strain, and electrochemical state. A distributed battery management system, BMS, that can isolate sections quickly is required for safety and longevity. Additive and automated manufacturing, multi-material 3D printing, automated fiber placement, and resin infusion techniques enable precise placement of active materials and conductive paths at scale. Modularity and demountable interfaces, mechanical and electrical connectors designed for safe disassembly allow replacement of damaged or end-of-life sections without destroying the host structure. Thermal management integrated into structure, embedded cooling channels, phase change materials, and heat spreading layers are necessary to keep cells within safe operating windows without undermining stiffness. Advanced coatings and separators, ceramic coatings, flame retardant interlayers, and robust separators reduce the risk of propagation in the event of a fault. Sector-by-sector integration strategies. Phones and small electronics. Phones and small electronics benefit most from space and thickness savings when the casing or frame stores energy. Manufacturers can use thin structural electrodes and solid polymer electrolytes as the phone chassis, which reduces internal volume for components and allows slimmer designs. Designers should place structural battery layers in parts that seldom deform, e.g., backplate and mid-frame, and incorporate flexible current collectors for ports and connectors. Because consumers expect replaceable batteries or long lifetimes, modular backplates or easily replaceable battery frame modules are advisable. Safety is critical, so redundant separators, thermal fuses, and robust BMS firmware are required. Consumer electronics and wearables. For wearables and devices with frequent mechanical flexing, semi-structural approaches are preferable. Flexible structural batteries embedded into straps, frames, or rigid zones can power sensors and displays while keeping weight low. Designers should optimize for cycle life and skin-safe materials and include wireless charging options to avoid frequent connectors. Buildings and architecture. In buildings, structural batteries can be integrated at multiple scales. Load-bearing panels, curtain walls, roofing, and floor slabs can store energy and feed building management systems. Prefabricated modular panels that are both structural and electrochemical simplify installation and future replacement. In high-value or energy-resilient buildings, carbon composite facade panels with embedded photovoltaics and structural batteries can create energy-positive envelopes. For mass construction, lower-cost cementitious structural batteries, cementitious matrices with conductive and redox-active additives could provide distributed storage, though they currently have lower energy density. Building integration must comply with fire, building code, and long lifetime requirements, so redundancy, compartmentalization, and serviceable modules are essential. Cars and light vehicles automakers can integrate structural batteries into the skateboard floor, roof, doors, and select chassis members to reduce mass and improve packaging. A practical near-term route is the partially structural skateboard, a stiff floor that contains large area cells and non-energized crumple zones up front and rear. The vehicle must include fast isolation relays, crash sensors, robust thermal paths, and modular service panels to allow safer repairs. Integrating motors and power electronics directly to structural battery anchor points reduces cabling, lowers parasitic losses, and simplifies assembly. Trains and mass transit trains are structurally large and can incorporate structural batteries in car body panels, floors, and roof sections to supply hotel loads, regenerative braking buffering, and last-mile off-grid capability. Structural batteries in bogie frames or underfloor modules must be protected against impacts and water ingress. Because trains operate on long lifespans, modular swappable panels can enable mid-life battery replacements without removing structural integrity. Aircraft and aviation demands the highest specific energy and strictest safety margins. For electric aircraft and structural batteries in wings, fuselage panels, and control surfaces offer great potential for mass savings. However, aerospace integration favors very conservative, redundant designs with rigorous qualification testing. Early aerospace adopters are likely to use semi-structural panels for non-critical surfaces and to combine structural batteries with hybrid systems, fuel cells, until energy density and certification maturity improve. Ships and heavy transport marine structures such as deck panels, superstructures, and interior bulkheads can incorporate structural batteries to power hotel loads and propulsion assist in hybrid systems. Saltwater-tolerant solid electrolytes and sealed, compartmentalized modules are crucial for corrosion resistance and safety at sea. Cities and infrastructure at city scale, structural batteries can be used in street furniture, noise barrier walls, bus shelters, bridges, and parking structures to provide distributed energy capacity, grid services, and resilience during outages. Integrating storage into bridges or noise barriers brings unique safety regulatory requirements, so pilot projects and clear maintenance regimes are prerequisites. Transport hubs, terminals, depots, and parking garages can use structural battery modules to smooth demand and support electrified fleets. Entire transportation systems and networks systems treats vehicles, tracks, roads, stations, and grid interconnection as one integrated energy and mobility ecosystem. Structural batteries distributed across vehicles and infrastructure reduce the need for centralized grid upgrades by providing localized buffering, peak shaving, and vehicle-to-infrastructure or vehicle-to-grid services. Fleet operators can aggregate distributed structural battery capacity for grid markets or resiliency services, but secure communications, standard APIs, and regulatory frameworks are required. Every other thing that's functional, for almost any object that has a structural element and an energy need, such as furniture, industrial robots, agricultural equipment, or medical devices, designers can embed energy in load-bearing parts to remove dedicated battery packs. The right integration pattern depends on expected mechanical loads, lifetime, safety, and serviceability. Lightweight, low-energy systems like sensors and actuators are the easiest to electrify structurally because they require less capacity and can tolerate lower battery energy densities. Safety, serviceability, and life cycle considerations. Safety must be designed in from day one. Structures with embedded energy need fast electrical isolation, robust separators, fire-retardant layers, and mechanical design that isolates sacrificial crash zones from energized regions. Serviceability requires modular panels, demountable electrical connections, and clear protocols for safe replacement and disposal. Designers must reconcile the differing lifetimes of structures, decades, and batteries, years, by enabling midlife battery replacement or designing for very long cycle life chemistries. Recycling processes and circular economy strategies must be built into product design to recover carbon fibers, metals, and active materials. Economic, regulatory, and social enablers. Widespread adoption depends on lowering material costs, notably carbon fiber and solid electrolytes, scaling automated manufacturing, creating certification standards, and developing repair and recycling ecosystems. Governments and industry must collaborate to create building and vehicle codes that allow structural energy storage while protecting public safety. Financial incentives, procurement policies, and pilot programs in high-value sectors, aerospace, defense, premium EVs, resilient buildings, will accelerate learning and cost reductions. Integrating structural batteries into phones, electronics, buildings, vehicles, and cities is technically feasible and strategically attractive because it can save weight, space, and materials while providing distributed energy services. To realize this vision, engineering teams must co-design materials, electrical systems, thermal systems, safety features, and maintenance procedures from the start. The path to ubiquity requires parallel advances in multifunctional materials, solid electrolytes, automated manufacturing, standards, and recycling. When policy, economics, and technology align, structural batteries will become a pervasive design pattern that helps make devices, transportation, and infrastructure more efficient, resilient, and sustainable.